Hello. So, shall we get started? Cool. Yeah. Lots of people coming in. Also, these lights are so bright. I can't see anything. Right, so welcome to this talk. We're going to be talking about HTTP history and performance. Very happy to see you here. My name's Anna. I'm your speaker. You can find me in all different places on the internet, including Twitter, where I'll be posting the slides. If you ever want to use them as a reference, go back and check something. I work at a small startup based in London called Verve as a senior software engineer. And I mostly do Python and Django. Django is a popular Python web framework. Any Python people in the audience? Ooh, yeah, nice, I love it. That's very cool. Just to make it clear, so I'm not like a network engineer or a web standards advocate or evangelist. I decided that I want to speak about HTTP because this is something that I found interesting, and I'm just a regular backend developer, no more than that. So when I came to the web, I've eventually found out about Hypertext Transfer Protocol, and I have an OCD in naming things, so I can spend hours just figuring out what is the correct variable name for something. So when I saw text, that kind of was a dissonance, because I'm pretty sure I can transfer not only text, but I can transfer audio and images and all sorts of things. So I thought it should probably be called Hypermedia. Well, in fact, it has been tried to rename HTTP to something like Hypermedia, but it never got changed. And the initial version, Hypertext Transfer Protocol, was a misnomer because the first implementation of HTTP, in fact, could transfer only text. So in 1991, Tim Berners-Lee outlined the basics of the modern web, which included HTTP and HTML. At the time, there was no RFC, no spec, but there was an implementation of a subset of the protocol, which later on we called HTTP 0.9. So interestingly enough, it is possible to speak to many servers in the wild, HTTP 0.9. As an example, you can telnet to some server on the port 80 and see how it's done. And so what we're doing here, we're going to telnet to Mr. Stallman's website. The server would tell us that we are connected to stallman.org. What we do next, I type in get, this is my request, a space, and the index. I want to access the index page. And when I hit enter, straight away, the server spits out all of the HTML and closes the connection. And this is it. The main features of HTTP 0.9 are the client request is a single ASCII character string terminated by a new line. It consists of words get, and in fact, at that point, the only verb that you could use was get, followed by a space, followed by the document address. The server response is similarly a byte stream of ASCII text marked up in HTML, or plain text if you wish. The response message is terminated by closing the connection. So you need a way to figure out that the server has sent out everything, all of the data that it had, and this is it, like this is the end. So how we do it, we just close the connection. This is the signal that you got all of it. There was no metadata. So you can't do any content negotiation either. So yeah, overall, a lot of things are not here, stuff that we are fairly used to in HTTP, but this protocol was fairly simple, and in fact, it was so simple to implement and follow along and get started with that it took off and actually became quite popular. So right after HTTP 0.9 was kind of released into the wild and developers started implementing the protocol on the servers and on the clients, works began on establishing a proper spec that became known as HTTP 1.0. and that happened in 1996. So let's forget about Telnet, because this is obviously a very insecure channel of communication, and let's use CURL. If you want to make a request using CURL in HTTP 1.0, you need to pass in the 0 argument. So let's fetch the homepage of Twitter. First thing, we connect to the Twitter server. CURL for us will inject the request headers. There is a get, / the protocol version. There are a bunch of headers like the host, user agent. We receive the response, which is made up of the response headers and of the response payload. The response headers will tell us the response status code, in this case 200 OK, and other things, for example, like content type. And then the response is a plain text HTML, and the connection is closed, similarly how it has been done previously. So there are lots of things going on here. So the request suddenly can consist of multi-line, new line separated header fields. It also includes the protocol version, because suddenly we started thinking about the future, because after 1.0 we probably want to have 1.1, who knows. The response object has its own set of new line separated headers, prefixed with a status response line. The connection between the server and the client is still closed after every single request. Response is not limited to hypertext anymore, so this is the breakthrough. We suddenly can have all the different content types. Exciting. And there's generally a lot of things that have been defined by the spec, for example, caching mechanisms and proxy behaviors and content type negotiation and content encoding. Lots and lots of things. Now, what we're going to do next is we're going to do some examples, and this is a warning. So we will be timing how much does it cost us to make a request to do a certain request response cycle, so essentially like the whole round trip. And we'll be using fixed synthetic values. We'll say the latency is going to be 30 milliseconds. Whereas in the real world, the networks don't work like that. They continuously fluctuate, so you don't get like a static latency. It's all kind of going up and down. So what do we have here? We have our client and we have our server. So as we said before, let's assume the round trip is 30 milliseconds. That's fairly low latency. It's not too bad. Before the client can start fetching data from the server, we need to establish a TCP connection, because most common use case how we run HTTP is over TCP. This is how the OC stack kind of works. So first we need to do the freeway handshake. The client sends a SYN package to the server. The server responds with a SYN acknowledge. The client responds with a acknowledge package, and it packages together with this also the request, so that it doesn't need to do another round trip. Now, the server spends some arbitrary time processing the request. Say there's a 35 milliseconds for our server to prep the response. It returns the response back, and then we close the connection. So in total, what happens is we spend one round trip for the TCP handshake, 30 milliseconds, and for the HTTP exchange, 65 milliseconds. Now, pages on the web rarely consist of a single resource. I mean, unless you're using something like links, text-based browsers, which are really cool and suitable for certain use cases, but most of the times, it's not the case. So in case of Twitter, to see the Twitter homepage, we would need to download, fetch 21 resources. And for that, we would need to wait roughly 2 seconds if we were to request it over HTTP 1.0. Assuming the time to first byte is actually faster, this is still far from being instant. Like generally, by our modern standards, this is kind of slow. And according to HTTP Archive, actually, modern day web pages are roughly consist of, on average, 100 resources. So that will make us wait for 9.5 seconds, which is kind of horrendous. But I actually lied to you. When I showed you the CURL request, it said connected to twitter.com on port 443, which means that we've made our request over HTTPS. And what happens when we do it is, on top of the TCP, freeway handshake, we also need to do the TLS handshake, which is another whole story, because we need to establish a secure channel for communication. And only after that we can start exchanging application data and do what we actually wanted to do in the first place. That concludes that to the one round trip for TCP, we have another extra 2 round trips for TLS. There's good news. TLS sessions can be resumed. So what happens in this case, we spend 1 round trip for the TCP handshake, and we spend 1 round trip instead of 2 round trip for the TLS session resumption. And then again, we can exchange the application data. Now back to the Twitter homepage and our 21 request, assuming that the first connection will perform the full TLS handshake, and for all the consequent requests, we'll use the TLS session resumption. That will give us 2.7 seconds. Again, going to the 100 requests per average page on the modern web, that's going to be 12.5 seconds. It is slow. It is very slow. Like that, considering that you have fairly good latency, that's 30 milliseconds, but a lot of people don't have these speeds. So no surprise that after releasing HTTP 1.0, RFC works began on HTTP 1.1. It was developed over a period of roughly 4 years, and the first spec was released in 1997, follow up with the extension to the spec, the RFC 2616, in 1999. And this is the default, this is what we have, this is what every single client and browser speaks. We never question whether it is HTTP 1.1 compatible. It's kind of there, and we really got used to it. So going back to CURL, let's make another request, this time to github.com. So, the same bunch of request headers, we make a GET, we've upgraded our protocol version to 1.1. We get some response headers, and we see some new headers, for example, like transfer encoding and cache control. This kind of sounds exciting and interesting. We receive our payload, and it tells us that the connection to host github.com left intact. We're going to talk more about that. So let's make another request. Also to GitHub, in this case, let's download the Octocat, because Octocat is super duper adorable. I've omitted the request. The only thing you can see when I'm invoking this URL command is that I'm passing another header, which is range. I'm requesting that I want the 0 from 1024 bytes. This is generally useful if you want to resume a download, or you read the tail of a growing object, or in the case of browsers, you might want to read, for example, just the beginning, the metadata of the image to figure out the size, and so you can start building out the layout. It's an interesting optimization. So let's take a look at the response of from the server. So we get a new status code that we haven't seen before, 206 partial content, and we get a bunch of headers like cache control and age and content range and content length and connection keep alive, which this is something interesting. We get our bunch of headers that we've requested, and again, the connection to the host left intact. So what's up with all of this connection keep alive? Well, connection keep alive is a really cool performance booster that we got, and I'm going to explain in a minute what exactly that means. What else do we have in HTTP 1.1? Well, we got compression and chunked responses and byte ranges. We also got something called pipelining, so that we can break from the strict request response cycle, and we're going to talk more about that. We have much better flexible caching mechanisms to improve performance. We got 24 new status codes, exciting, like the one we've seen with the partial content. And we get cookies. Even though the web was supposed to be stateless, we actually wanted it to be stateful, so we ended up with cookies. Right, so remember we talked about the TCP freeway handshake. Well, what happens with the keep alive connections, which are, by the way, by default on in HTTP 1.1. So we do the TCP handshake once, and then we request a bunch of data, and then on the same connection, we just request other data, and we just keep on doing that until the connection is closed due to a timeout or some other reason. So this is a really cool thing that we got with HTTP 1.1, because suddenly we can reuse those TCP connections. We don't have to pay this extra round trip for the TCP handshake and for TLS every time we want to request another resource. So what happens, going back to our synthetic network calculations, and assuming again that we're making a request to Twitter homepage, now using HTTP 1.1 with TLS handshake, we need 1.5 seconds to download 21 resources. For 100 resources, the time went down to 6.5, and previously it was 12. So that kind of looks impressive. That's roughly 20% increase in speed for secure requests from HTTP 1.0 to 1.1. Though, to be noted again, this is all synthetic calculations. So in a real-world example, you could get sometimes better performance, sometimes worse. It really depends. But if you're kind of in a vacuum and you just look at these values, you get much better performance due to keep alive connections. In reality, what happens is that we're not waiting for 6.5 seconds for a page to download on average. If we got good latency, this is going to happen much faster. Reason being, browsers are not simple socket management apps. They're actually quite smart in doing a lot of things. And one of the smart things that they do is that they open 6 simultaneous connections per domain. And this number can vary based on the browser or a setting, but 6 is kind of the general magic number. So if you go to the waterfall model in the network tab, you can see how 6 requests are dispatched in parallel, and then another 6 requests are dispatched in parallel. And if you want to see the clustering of these, what you need to do is you need to sort by priority. If you don't see priority in your network tab, right-click and take the priority. This is the same place where you can find if you want to see what protocol, what protocol in general the client and the server are using to exchange data. So in this case, you can see that the client downloaded the page and started parsing it from top to bottom and discovering resources. It fires up the requests where CSS and JavaScript become the top priority because they will block the rendering of your page, and everything else is kind of lower priority, things like images. Now, this is probably a good moment to talk about head-of-line blocking. Head-of-line blocking means that each subsequent request has to wait for the previous request to finish, so it's all very consecutive. It's like a line, so it just goes one after the other. You can't make the request for the JavaScript until you've got the response for your HTML document. Now, if something happens with the HTML response while it is in transit, is not only you won't be able to download to fetch the HTML document from the server, but also all the subsequent request responses won't be executed. So everything else in the pipeline is kind of waiting there and is unable to be fetched. And you're just looking at your browser and it's spinning to infinity. So I've mentioned pipelining, which pipelining was kind of those things that is like, ooh, we know how to solve head-of-line blocking, let's try and do it, because we've obviously been aware of this problem for a while. Pipelining is a mechanism that will allow us to break from the strict request-response cycle. So what happens is after the TLS handshake, the client can request multiple resources at the same time. So in this case, a document and a JavaScript. And just fire them at the same time. without waiting for the response to come, for the first response to come back. And hence, in this case, make better use of the server time. So the server will will acknowledge for the pipeline request. So it will prep the response for the HTML, it will prep the HTML response and the JavaScript response. It sounds great in theory, but why we haven't been aware of the pipelining as much, and why the question is, why is it disabled in browsers actually by default, is because parallel processing on the server introduced subtle implications, and because it required like strict serialization of response, and actually pipelining sometimes introduced worse performance or didn't bring anything better to the table. There are some use cases of good use of pipelining, but it's mainly when you control both the client and the server. Right. Let's have a chat about HTTP servers a little bit. So in HTTP 1.0, 1.1, and both 1.0 actually, HTTP headers are textual. So the average request will have from 700 to 800 bytes. It can explode up to 2 kilobytes, usually because of the cookies. Cookies can become quite lengthy. And it doesn't seem like it is as much, but it is an overhead that every single request response incurs every time. So even though we perform optimizations and compression on the response message, headers generally remain uncompressed. So talking about bundling and minimization, they're like second nature to us. We religiously put everything in one big file, and we concatenate it, and we try to make it as small as possible. Because based on the learnings of how HTTP works, assuming it is on top of TCP, this bundling and minimization makes a lot of sense. We minimize because the fastest byte is a byte not sent, and we concatenate because we can reduce so much of the protocol overhead, all of the handshakes, all of the header bytes, all of that. So it's similar to doing pipelining, but it's just we're doing it at the application level. So reducing the number of total requests is one of the best performance optimizations. Spriting is a very similar hack/trick. This is a sprite I took from Amazon homepage. So instead of fetching every single tiny resource separately, which would be very, very expensive, we put them in one big file and set it all as one. But we shouldn't fool ourselves that this comes at no cost. This brings some of the issues. So with bundling and minimization, we have a certain complexity in creating them, so we're actually pushing the complexity from the protocol level to our application level. We have potential caching problems with bundling, similar with bundling and minimization and sprites. Once one of these tiny resources or one of those tiny JavaScript files changes, we actually have to flush the whole cache and refresh it instead of just refreshing the one part that has changed. And with sprites, for example, the browser has to keep all the image in memory. So the reason why everybody started paying so much attention to HTTP as a protocol is because of HTTP2. So the basis of HTTP2 is another protocol called SPDY or SPDI. It's an experimental protocol developed at Google. And engineers at Google had several goals in mind when they were developing a SPDY. They wanted to reduce the latency of web pages. They wanted to minimize the cost of deployment complexity and to avoid any changes in the network infrastructure, because this is something that we actually cannot change. We're not going to go all over the world and change every single router, switch, and everything just to kind of like erase what we had previously and start fresh. This is not how the real world works. So in 2015, it has been drafts for HTTP2 and HPAG have been approved, but the work is still ongoing. So HTTP2, also how the cool kids call it, H2, is really, really cool and full of wonders. If I were to do a CURL request, and by the way, CURL can speak HTTP2, then for the outside observer, not much would have changed. You would see the same request-response cycle, the same headers, status codes, the keep alive connections, all of this is there. But for us to understand what is the difference between all the previous versions of HTTP and H2 is we need to look underneath, we need to analyze the packets. So what we do, we fire Wireshark, and once you're able to decrypt your traffic, because HTTP2 will be served over HTTPS only in browsers, and we filter our H2 traffic, we can see new types of packets, which are actually, we're going to learn, they're called frames. So going top to bottom, we have a window update, settings, headers, data, ping, on and on. So the key differences between HTTP2 and its predecessors are that it is a binary protocol instead of a textual, so it introduces a binary framing layer. I'm going to explain more on that later. So because of that, it will allow full multiplexing of requests and responses. We can also do server push. In other words, the server can proactively decide to push some of the resources to the client. Similar to TCP, that can do flow control. Now we can do flow control at the HTTP, at the application level, HTTP. And due to multiplexing, we only need one connection per origin instead of 6. It has been proven empirically that one connection is enough, so you don't need to open more. You won't gain any better performance if you're using HTTP2 and multiple connections. And H2 also introduces header compression to reduce overhead. It's actually not HTTP2, it's actually HPAG, but we're going to talk about that soon. So, binary framing layer is the key to a lot of features that are possible in H2. If we look at the previous versions, like HTTP 1.1, what we did, we had a convention. We said the first line is going to be our request, where we say the verb, the document, address, we say the protocol version, and then for each new line, we're going to have a request header. And when we have 2 new lines, this is how we separate our headers from our payload. And this was just a convention. With the H2, we get something else. So H2 messages are encapsulated in a specific way, and we get these frames. And there are different types of frames. There are 10 types of frames. We've got headers. Headers are obviously there to send headers. Data is to send payload. Settings to negotiate various configuration parameters between the server and the client. Ping to measure the minimal round trip and go away to initiate the shutdown of a connection. And basically, because of that, because we suddenly have HTTP2, which is a binary protocol, it's suddenly not compatible with the previous version, and that's why we have a whole version increment, and we don't have an HTTP 1.2, but we have an H2. So, multiplexing. Multiplexing, in essence, means that we allow multiple requests and responses to be in flight at the same time. It is something very different from what we had before, where we said we have a very strict request-response cycle. We send the request, we wait for the server to do the processing, the client just kind of doesn't do anything. Meanwhile, then it receives the response, and only after that it can send another request. So how does it work in more detail? So let's imagine the whole canvas is our one single connection. You could think of it as a TCP connection. So the connection can carry multiple streams. Streams are virtual. They don't exist physically. There's no separation in the physical world that will tell you this is stream A and this is stream B. They're all kind of just all in our mind. And the number of streams can be quite high. I think it's up to 2 billion or so. So streams are bidirectional channels of communication that roughly will translate to like a request-response cycle. And each stream can carry a number of messages. Messages identified to their stream via the stream identifier. This is kind of where the whole virtual part comes in. And messages themselves are composed of frames. So when I'm making the request, I've got a headers frame, and when I'm getting a response, I'm having some headers and some data, for example. And that's pretty much it. What happens is that while the client on the stream 1 might be sending a request, on the stream 2 it might be getting some responses from the server. And we can have many more streams initiated to initiate all of those different exchanges and to interleave requests and responses in parallel without blocking on any one of them. Because we have so many streams, as I said, you can have up to 2 billion, we need to have something like a stream prioritization. Each stream may have a weight, and it can be dependent on another stream. In concept, this is similar to what browsers have been doing. They were assigning some internal priority to all the different resources and saying that style sheets and JavaScript are going to be of higher priority than the images. But now you actually can do it yourself with the stream prioritization if, for some reason, some images are going to be more important for you to be downloaded rather than the other images. And due to multiplexing at the application level, we actually don't want to overflow either the client or the server. So we need a way to tell either of the parties to back off. So that's why TCP flow control is not good enough for this. We're introducing HTTP flow control, where both the client and the server are negotiating and are setting their desired window size, which can be shrinked or expanded. Right, so let's talk about server push. So if you think about it, if you're a client and you're requesting an HTML document and you're not a links browser, you probably would want to download all the other resources for this page to render properly, like style sheets and JavaScript. So it kind of makes sense that you probably need them. This is the idea behind server push. So if the client is requesting an HTML document, what the server can do in this case, the server will prep the response, but it will also, meanwhile, initiate a couple of other streams with some frames called push promises. So your application server can decide that if you're requesting index.html, you probably want to also download script.js and maybe also the style.css. So what the server does, it opens up extra 2 streams and it sends those messages to the client. And it's important that the push promise frames reach the client earlier than the response itself, because we don't want the client to grab the response, start parsing it, and then sending the requests straight away, because then we'll create duplication. Now, once the push promise frames reach the client can either accept them or reject them by closing the stream, I think. This is just a conceptual model of how server push works. How you're going to apply it in the real world is a totally different problem and probably would require a talk in itself, because there are multiple problems that you would like to solve. What if the client has the resources cached and probably doesn't want the push promise at all to happen? What about the security? What about the overflow? Well, we have the TCP, we have the HTTP flow control. there are some proposals where you can use the link header with like a preload so that you can negotiate this better. Would you like to push all of the resources at the same time, or maybe you just want to be more granular? So I think there are a lot of questions that people are still asking and experimenting with in terms of server push. But in general, this is the idea of how it works. Right. So we said that HTTP headers represent an overhead, especially when we've got fairly lengthy cookies. In H2, this is solved using HBAC, which is a compression format specifically designed to work well with HTTP headers. It is composed of 3 main components. So we've got a static table. It contains 61 commonly used HTTP headers. We have a dynamic table that is initially empty but will be populated with new headers for the duration of the connection. And the rest of the headers that are not indexed, so they can't be found in the static table or the dynamic table, will be compressed, encoded, using a static Huffman encoding code, which has been statistically obtained on a large sample of HTTP headers. And so this is how it's going to work. When I'm making my first request, and if I'm not using HBAC, what will happen, I'm just going to send all of these headers as they are with no compression. Now, if I'm using HBAC, the common headers found in the static table will be encoded each with 1 byte. So things like method get and scheme HTTPS and path/, these are very, very common headers. We use them very often. They can be found in a ton of requests. Also things like sometimes we just know that accept or user agent without the other part, the value of the key value pair, can also be encoded with a single byte. So everything marked in green is what we can encode with a single byte. All the leftovers, which were marked which remained in black, will be encoded with a static Huffman code. In addition to that, we're going to grab the key value pairs of the headers that were just now encoded using Huffman, and they will be appended to the dynamic table. What is happening now is we're going to save the cookies, which are probably quite lengthy, in an index table, and we will save precious bytes for all these subsequent requests. So when I'm going to do my second request using HBAC, this is what is going to happen. We will encode using the static table. These are all the headers which are marked in green. So again, method get, scheme HTTPS. We will encode using our dynamic table headers that we have recently inserted in. These are pink purplish kind of color, things like user agent and cookie and host. And the rest of it is going to be encoded using the Huffman code. Believe it or not, but this kind of compression can reduce from 30 to 80% of header bytes. And I think this is quite impressive. So let's think about all of the previous best practices / hacks that we've been using in previous versions of HTTP. And how do they translate in the world of HTTP2? So we used to have 6 connections per origin. This is no longer needed if we're using H2. So 1 single connection is enough. Hence, we also shouldn't be doing domain sharding. Domain sharding was something used for websites that desired to have more than 6 connections. So they would shard their domains, and would trick browsers into thinking that they can open not 6, but maybe 12 connections at the same time. So this doesn't make sense anymore. Inlining resources is generally not necessary because of multiplexing and server push. And also, once we are not inlining our resources, we can actually cache them. So I think this is a benefit that we're getting. Naive concatenation of assets. So Bundled assets, we said, result in more expensive cache invalidation and delayed execution and unnecessary transfers for some of the pages. But smart concatenation still makes a lot of sense because A, data can be better compressed if it is bundled, and B, even though the requests are cheap, they're still requests and they still carry some overhead. So we should keep that in mind. The similar idea applies to sprites. Your app needs to find the right balance between putting everything in one bin versus spawning hundreds of requests for each tiny resource. So these things kind of should find the right way to use them. What does still make sense in the world of HTTP2? Well, these are called evergreen optimizations. So regardless of the HTTP version you're using, there should be there and you should be thinking about them. So you need to have a fine-tuned TCP stack, make use of smart caching, use e-tags. Caching is always a fantastic way to optimize your app. Use CDNs because servers, placing servers geographically closer to your users will reduce the latency, and this is not only a problem for some of the more remote countries, but maybe like first world places, it can still be a problem. Think about Australia. I think they have horrendous latency, and it's very painful to navigate the web if you're there. So eliminate unnecessary resources. If you don't need something, just don't put it there, don't download it. Extra latencies for no reason is generally no fun. Always compress your assets, regardless of the HTTP version. Compresses reduces the number of bytes on the wire, and this is what we are generally trying to do. And maybe try to reduce your header bytes. Mostly think about cookies. Maybe don't carry so many cookies with you along, but generally hooray for HBAC. Right, let's talk a little bit about statistics. So this is a chart replicated from a presentation given by Patrick Hammond on HTTP2. And even though it has been quite a long time, because this presentation was given in March 2016, I think the data from there still applies. So he shared some stats on the impact of latency and HTTP versions on the financialtimes.com website. So what we can see from here, and as you can see, the blue line, that's HTTP 1.1, and the orange one, this is HTTP 2, is that for users with low latency, say under 100 to 200 milliseconds, you can't see much benefit in switching from HTTP 1.1 to H2. It kind of seems the same. But H2 truly shines once your latency becomes much higher, so you can see a big impact based on that. Also a bit of the outdated stats, but again, couldn't find anything more fresh than that. So last year, that's roughly a year ago, Mozilla at FOSDEM shared some traffic stats anonymously shared via the Firefox browser. So if we're looking at all of the traffic that goes through Firefox, it says that roughly 30% of it is served using H2. I found some other data. There's a website called W3Tax. They have all the different statistics about the web, and they claim that currently 23.2% of all the websites are using HTTP2, and this is this year. And last year they said it was roughly 11. So maybe all of the Firefox users are all very HTTP2 savvy. I don't know, because they had 30% last year. But this doesn't look too bad. But if we take into account that HTTP2 traffic can be if we take into account only HTTPS traffic, based on the idea that H2 can be deployed only via HTTPS, because otherwise you can't do it, it's disabled in the browsers, we're seeing that it's actually 60% of the traffic. The reason being is most visited websites like Google and Twitter and Facebook, a lot of them are served partially or entirely via H2. And whereas if we take a look at the top 10 million websites, then this is going to be 12%. I think regardless of that, it looks like a very nice trend. Talking a little bit more about HTTP2 stats. So Fastly did a presentation, and you can find it online. They've got a whole bunch of slides on the different experiments that they ran, comparing the performance of different HTTP versions. And this is some interesting insight that I found out when testing HTTP 1.1 and HTTP 2 in different scenarios. So in this case, what we're testing serving a website in Firefox. We've got 40 milliseconds latency and 0 packet loss. So the website loads faster over H2. H1 is lagging behind. Again, this is the blue line. And this kind of matches our expectations. From everything we've learned, HTTP2 should be this silver bullet that is just going to be like, everything's going to be so much faster and a lot more amazing. Now, we are running the same test. We also do Firefox, 40 milliseconds latency, but we're introducing 2% packet loss. And H2 performs poorly. The page will load faster in the browser over HTTP 1.1. You might be having a question, why is that happening? Even though HTTP2 eliminated head-of-line blocking at the application level, head-of-line blocking still exists at the TCP layer. So TCP as a protocol, it's reliable and ordered and kind of wants you to make sure that you've received the packet that it has sent. This makes it prone to the problem that we have just discussed, which is the head-of-line blocking. Another question, why this didn't happen for HTTP 1.1? Well, it probably did happen, but because in browsers, when we're running HTTP 1.1, we are opening 6 simultaneous connections. Well, some of them will succeed, so you're not actually blocked on one single connection, so you're going to open multiple. So yeah, 6 connections in HTTP 1.1 actually performed better than H2 with 2% packet loss. This is where Quick comes into the spotlight. Quick is an experimental transport layer built over UDP that very much doesn't resemble UDP, apparently. It resembles something more of a TCP plus TLS plus H2 implementation. It is considered to be a step forward in eliminating head-of-line blocking problem at the transport layer. And I think we're yet to see the finished drafts of it, and maybe, who knows, the widespread adoption in the future. If you want to learn more, I highly recommend this book. This is High Performance Browser Networking by Ilya Grigorik, an engineer from Google. It talks not only about HTTP, but all the different components that make up the web. It has a great chapter on mobile networks, and it explains in a lot more depth all the different things about H2 and latency, and why latency is more important than bandwidth. So highly, highly recommend it. And this is it. Thank you.